And
wait, Richard. Hold on, Richard.
Okay. Now it's good then?
Is the recording going?
I think so.
Yep. Excellent. Okay, so for the second talk of the session, we have Rachel Lin from UW, who's going to talk about non-interactive secure computation. So Rachel, looking forward to the talk.
Thank you very much. Thank you, Dan and Amit, for organizing this workshop and for inviting me. And hi, everyone. Good to see you here. So our talk about the Mr. NISC, it's a weird shorthand. Finally, one time that I wrote a paper that has a very nice and cute acronym. But that's not the focus. The focus, what is Mr. NISC? I want to tell you about that in today's talk, and hopefully it will make you excited about this concept and you will work on it. And so there are multi-party, reusable, non-interactive secure computation, and hence the shorthand Mr. NISC. And this talk is based on two works. One is with Fabrice Banhamode at the TCC20, and the other is with Fabrice, Ayush Jain, and Ilan Kolmogorski at the Eurocrypt 21. Okay, so we are all very familiar with the concept of secure computation. It is a remarkable concept proposed in the 80s, and it has been extensively researched until today. And here, the context is that we have a bunch of parties that they hold confidential data sets. They could be medical records, and they need to be kept private and not shared with each other. And the goal is that we want to jointly compute, enable them to jointly compute a function and reveal nothing beyond the function. And we typically think about adversaries where it could corrupt some of the participating parties and observe everything that happens during this computation with these honest parties. And what we want is that even with these observations, all the adversary can learn is the output and its own input, which it always knows, and know nothing else beyond about the honest parties' inputs. Okay. So since the concept of secure computation, it's the most natural thing to wonder whether we can do this remarkable thing non-interactively. So the vision of non-interactive secure computation is that to do what I just said, that parties can just compute a function and learn nothing beyond the output, but only requiring each of the participating party to send one message. And those messages do not depend on each other. The only thing the message depends on is the party's own input. Okay? If I can do that, that's very flexible and it's very appealing. Unfortunately, very early on, we already noticed that this is not possible because inherently any protocol, no matter how smart we are designing those one message for computation, there's always gonna be some leakage of the residual function. How an adversary observing those messages alpha 1, alpha 2, alpha 3, now can just imagine that it is acting as the first party and have a different input x1 prime. From x1 prime, it can compute a different computation message alpha 1 prime. And from this, combining with alpha 2 and alpha 3, it should legitimately learn what is the output of the function. Now the first party's input has been swapped from x1 to x1 prime. Now once we notice this, we see that it's not just a single x1 prime. In fact, any x1 prime, that adversary can do this attack, and effectively it has access to the residual function where x2 and x3 are hard-coded. And this is not the promise that we want. We wanted the only thing revealed is the output of a single computation that is admissible, that is allowed. So is all lost? The theme today is that what about we can consider non-interactive secure computation, but now over encoded secret inputs? What we're thinking about is that parties holding their private inputs have access to a public dashboard. What they will do is that they will first encode their inputs using some secret. Each of the encoding is now denoted as xi hat, and they will simply publish these encodings onto the public dashboard and keep their secret S1, S2, S3 secret. So now from now on, whenever they want to do a computation of function f, they can send just a single message. But now this single message can depend on each party's secret state, but also all the input encodings of the participating party in this computation. Now, they just still only need to send a single message for a computation. The only thing that's different is this single message can now depend on the encoding of the input. So this immediately defeats the residual attack that we have just saw. How? Now imagine the adversary again trying to play the trick of imagining a different x1 prime and computes an alpha 1 prime, which it can do if it is actually corrupting the first party. However, this alpha 1 prime now is incompatible with honest party's computation message alpha 2 and alpha 3. Why? Because alpha 2 and alpha 3 actually depends on the input encodings that have been published on the public dashboard. So when the adversary wants to swap the input to x1 prime, it will be detected. In some sense, it doesn't match with alpha 2 and alpha 3. Okay, great. But is this just sort of, we now seems to have getting one step closer to non-interactive secure computation, but we want more. We want these public encodings to actually be reusable and can be reused over and over again in many, many computations. And this is why we call it multi-party reusable non-interactive secure computation. Now imagine all the users publish their input encoding in the public dashboard. Whenever a subset of those parties wants to do a computation, now they can just send a single message and learn the output and nothing else. Now a different subset of parties wants to do a different computation. Now they can reuse those encodings that they have already published in the dashboard and again send just a single message. And from those messages, the output can be recovered and nothing else. Now, parties can also dynamically join into this public dashboard, and they can come along and just publish their input encoding on the board. And then they can on the fly do any computation they want. So in some sense that Mr. NISC enabled this very flexible, sort of almost like a marketplace for multi-party, for secure computation. At any moment, any subset of those users can compute, and users can join and leave at any time. And we want those computations to have no restriction on which set of parties are computing or even how many parties are computing. In other words, all those input encodings are independent of any of the later information about the computations.
Rachel, can I just ask, is the function f public? Like the parties know the function f, or is it private?
Yes, the function f are public. So we're imagining that those encodings are public, and at some point, you know, these subset of parties decide they want to do a computation of f, and everybody knows that, and then they can generate those encodings.
So in fact, anyone can compute. Once the alphas are public, anyone can compute the function f. And so
exactly.
The whole world learns the result of the study.
Yes, the whole world will learn. Yes, if they see those messages were publicly revealed output.
Yep, perfect.
Okay. Yeah, that's a very good point. This is actually one kind of one little bit subtle bit that's different from secure computation. Sometimes that the output is only privately reconstructible. And here we want public output reconstruction.
I have one more question. Can the function f be randomized?
Can the function be randomized? So we are thinking about the function as a public circuit. So if it's randomized, then maybe it is that the input of the parties have a part which is the random coin. Maybe it contains a pure F key, then they can generate random coin, then they can compute the function and produce a sample from this output distribution. Is that what you're asking, Amit?
Yeah, I was just asking if there's like a, just like we have, functional encryption for randomized functionalities. There's some subtleties in the definitions and all that. I don't know if you guys have thought about that yet.
You're absolutely right. So with the current way that we defined it, I think function F is deterministic. The way I describe using PRF keys is sort of an intuitive and natural way of trying to accommodate randomized function by giving a way to secretly generate those random coins for sampling. But you're right, one has to be more pedantic and more meticulous in checking the definitions and so on.
Sounds good. Thanks.
Okay. Yeah, I really like interaction. So if any of you have more questions, feel free to just speak up during my talk. Okay, so a little bit more detail. Mr. NISC involves 3 algorithms. The first algorithm is the input encoding algorithm, where we can encode the input into an encoding that hides the input and using a secret. The second is a computation algorithm, which given a set of parties, which is denoted as S, that want to compute together a function F, that we use the encodings, their public input encoding, and each of those parties take its own secret and produces a computation message, alpha I. And finally is a reconstruction algorithm, which given all the computation messages and the function F will be able to reconstruct output, and this output reconstruction is public. Everybody can do that. Okay. So once we have these 3 algorithms, we'll have the Mr. NISC scheme and protocol. In terms of security, the important thing is that we can run the computation and the reconstruction over and over again for different functions using the same input encodings. When it comes to security, we really want the strong classical standard security notion for secure computation, that ultimately the only information revealed is the outputs. So let's think what an adversary corrupting a set of users C would see during lots and lots of computation. Well, definitely will see its own input and randomness. It will see honest parties input encodings that are in the public dashboard. And for each of the computation that happens, the adversary will see the public function F, as well as all the computation messages that are being sent to reveal the output. So this is what the adversary can see during lots of computation. And what we would like to say is that all these things reveal nothing beyond the output of the computation, the function itself, and the set of participating parties, i.e. the only thing that's revealed is the public information. And there are lots of computations, so there is this information for each of the computation. So we want everything the adversary can see can be simulated efficiently from this information. Okay.
Wait, why is XI, RI part of the input to the simulator?
And they're corrupted parties inputs.
Okay.
Yeah. Okay, so in the paper that we also define the security in a more sophisticated way that accommodates adaptive choices of the inputs and the adaptive choice of the computations, as well as we show that we also prove security against the semi-malicious adversary, not just semi-honest adversaries. Okay, we also give a kind of a UC security definition, but here is the simplest version that captures what we want. So in some sense, another view on Mr. NISC protocols is it gives us those 2-round multi-party computation protocols that has reusable first round and also dynamic sets of parties, where the first round is basically the broadcast commitments or encodings of the inputs, and the second round is to broadcast these computation encodings. So what do we know about Mr. NISC? Can we actually achieve it? So this notion was formalized in the first TCC paper that I had with Fabrice. And in that paper, we constructed using pairing with assumption SXDH. And prior to our work, we noticed that there are past 2-round MPC protocols that are based on strong assumptions like indistinguishability, obfuscation, or witness encryption, And we can observe that those protocols already have reusable first message, and their first message can also work with dynamic sets of parties. So they also give us Mr. NISC, albeit that their assumption is a bit stronger. And in a follow-up work, we constructed Mr. NISC based on lattices, LWE. And concurrent to our works, there are two more works that constructed reusable multi-party computation using LWE and decisional Diffie-Hellman assumption, with the slight weakening that they only work when the set of parties is fixed. So we have a set of parties who publish their first message, and from there on, they can repeatedly compute, but their first message cannot be used when they want to do a computation with a different set of parties. So it's a slightly weaker notion. What I want to tell you today is mostly about this construction based on lattices, how we can actually achieve all the desiderata we have mentioned. Okay, so what is the overarching view? In the classical paradigm of doing secure computation, we know that it is actually equivalent with this much weaker object called the OT, Oblivious Transfer Protocol. So OT is basically secure computation, a special case of secure computation for a very specific function that we want to compute. And we know that it is also sufficient for computing arbitrary function. So when we move to Mr. NISC, we consider a similar paradigm that we look at a specific function, which we call functional OT. And if we just have Mr. NISC protocol that implement this functional OT function, then we will be able to bootstrap and get Mr. NISC for any function. So what I want to tell you about is first, what is this classical paradigm, just to remind ourselves, and then move to tell you how we can generalize and extend to do Mr. NISC. So hopefully we're all very familiar with this classical paradigm that once I have oblivious transfer and gobble circuits, we can do two-party secure computation. And essentially gobble circuits allow us to scramble a one-shot computation, right? By one-shot computation, what I meant is I have an input, I have a circuit, and in one shot, it computes the output Y. Now to scramble it means that I will pick a bunch of random labels, a pair of those random labels for each of the input bit Xi. And I will scramble the inputs into these corresponding labels where the I's inputs translates now to LIXI. Correspondingly, I can scramble the circuit into a C hat, which we call a gobble circuit. The magic thing is that this scrambled input and scrambled circuit actually computes the right output. And if we look at the input, which by itself, they are random, and then look at an intermediate computation outcome of this gobble circuit, they all look random. And therefore, the only thing that is revealed is the output and nothing else about the circuit and the input in the computation. So once we have this powerful gobble circuits, to do a two-party computation between two persons, P1, P2, with their private input X1, X2, and we want to enable party 2 to privately reconstruct the outputs C evaluated on X1 and X2. A natural attack to do that is to basically let P1 gobble this circuit, which has its own private input hard-coded inside, and send over the gobble circuit. Now, the only thing remains to be resolved is how can P2 obtain the gobbled labels? But we notice that these gobbled labels actually depends on secret information, partly that belongs to P2 and partly that belongs to P1. And hence this oblivious transfer is essentially exactly what we need to do this label translation. It will allow P1 to input its two random labels, P2 to input its choice bit, and the P2 will learn from the oblivious transfer exactly the right label corresponding to its bit. And once we can do that, great, P2 can evaluate the gobble circuit and learn the output. So this is all fantastic, and this was one of the greatest contribution of cryptography since the 80s. The limitation is that it handles a one-shot computation, right? And what if I want to gobble now an interaction? What do I mean by an interaction? The P1 and P2 again has their private inputs, and now they're not one of them is computing a single circuit. Actually, each of them is evaluating a sequence of circuits in order to interact with each other. So P1's circuits are going to generate message that it will send to P2. And P2 circuits are going to generate message that it will send to P1. So in other words, that at each of the step, let's look at these steps, that the circuit that the party is evaluating is taking the message from the other party produced by the previous circuit and therefore generate its next message. At the end of the computation, that the last circuit is going to produce P1 and P2's final outputs, Y1 and Y2. Okay, so this is an interaction. Interaction is great, but interaction also takes time. Can I now actually gobble an interaction? Great, we have gobble circuit, why not try them? So let P1 generate a bunch of gobble circuits, one for each of the circuit that it is evaluating. So now these C11, C21, C31, they are all gobbled. And we should think about that P1's secret input X1 is hard-coded inside these gobble circuits. And so are P2's private input X2. We would like to say that these gobble circuits can talk to each other, that they can, again, produce the output of the circuit, which are messages, and send to the other gobble circuit produced by the other person. And so they can continue this interaction, but everything now is all non-interactive. There's no more interaction needed. The issue is obvious, is that gobble circuits don't take plain inputs. They only take labels, the scrambled inputs. So this communication channel is in some sense broken, that the gobble circuits actually cannot talk to each other. So therefore, when we want to gobble interaction, the key is to come up with a translation mechanism that can translate one person's message into the other person's labels. And this isn't completely easy because this translation depends on secret information held by two different persons, right? P2 is the person who can produce M12, and P1 is the person who knows what are the two choice labels for the label. And there must be some sort of non-interactive secure computation happening in order for this translation to occur. So this is why that oblivious transfer is no longer sufficient, because oblivious transfer can do the label translation, but it will require interaction, and it will require sequential interaction for each of the translation that is happening in the interaction. So the question is, can I actually do the label translation in a non-interactive way? If I can, then I can truly have talking gobble circuits. So that's why we formulated this enhanced version of oblivious transfer we call functional oblivious transfer. Here, the two persons have secret X1, X2, and they will input them to the function. And in addition, this function will take public functions, G and F. So similar in the format like Mr. NISC, that a public function comes along that specifies concretely what is the computation to be done. These public functions implicitly defines the two labels for oblivious transfer. They are computed as G evaluated on X1. It also implicitly defines P2's choice bit, which is F evaluated on X2. So now the output of this function is a public output, which basically gives the choice bit and the label chosen by it. Okay. So this is very similar to OT, but also much stronger in the sense that the labels and the choice bit are functions of P1 and P2's private inputs, X1 and X2. But other than that, what it essentially is doing is basically choosing a label, choosing a secret label. So a reusable functional OT protocol is basically a Mr. NISC protocol that implements this function. How would it look like? It would look like that the parties have a way to encode their secret input X1 and X2 and publish them. And whenever some public function G and F comes along, they can now generate those computation message, alpha1, alpha2, and from there, they can reconstruct the secret label and the choice bit, and the reconstruction is public. Importantly, they can do this label exchange many, many times for arbitrary public and input public functions G and H. So this is what Oblivious trans. Yeah.
Sorry, wouldn't you essentially want this G function to be randomized in some, way?
The G function is going to be a PRF.
Okay, good.
And X1 is going to be a PRFP. You're jumping ahead of me a bit.
Okay, sounds good.
As usual, yeah, okay. All right, so once we have a protocol, Mr. NISC protocol, this is how a Mr. NISC for FOT look like, and we call this protocol reusable functional oblivious transfer. And it's a very appealing primitive, and we hope that this will find other applications as well. But for now, let's see how this primitive can now enable the Gobble circuits to talk to each other. Coming back to the task, that let's focus on one translation. Here is that C22 produces the message M22, and we want to translate it into label for M22, where label is for the next Gobble circuit C31. Okay. So what are the labels for M22? So we're sort of mapping it to FOT now. So basically the choice bit is M22, and the label should be some label chosen by B. So first is, let's think that P1 is going to generate those possible labels L30 and L31 to be chosen from using a PRF with a secret key K1 and evaluate on some public input, here say 3. So in other words, the labels now is a function evaluated on the secret PRF key K1. And what about the choice bit? Well, M22 by definition can be computed by C22 with the secret input X2 hard-coded inside evaluated on message M11. So in other words, it by itself is some function F evaluated on P2's secret X2. Okay, so this basically gives me the function G and F as well as the secret input. Therefore, I can use FOT to compute it. P1 should input K1 and P2 input X2, and G and F can be learned in the public, and then they can compute the exact right label and the choice bit. So in other words, I can solve this translation task using FOT. So when we have a Mr. NISC protocol implementing this function, now we can do this translation non-interactively. How? I know that it gives me a way to publicly encode the secret PRF key and the input, private input X2. Whenever I want to compute the right label, all what I need now is the right computation message, alpha1 and alpha2, corresponding to this function G and F, and depending on the public encoding K1 hat and X2 hat. So the question is, once I have this computation message, I know I can publicly reconstruct the right label. So the question comes to, who is going to generate those computation message? Well, we can just let those Gobble circuits, modify the Gobble circuits to let them generate these computation messages, right? So we're going to now Gobble a slightly different circuit which not only is going to compute the message like before, but also the computation message that enables label translation. How come that this is possible? Well, remember that to generate these alpha 2 and alpha 1, that basically we want to make sure that these gobble circuits have the knowledge of the public function G and F. And knowledge about G is everyone has. Knowledge about F, no problem. Why? Because the previous message we can think about, it has already been sort of generated and both gobble circuit can know. Okay, so this gives a way to create gobble circuits who can just talk to each other, and also give us a way to construct Mr. NISC protocol for arbitrary function. What parties should do is to publish encoding of their private input as well as encoding of a PRF key using the reusable function OT protocol. Now, when a public function F comes along and they want to compute it, the idea is that they're going to take a many round secure computation protocol for computing F and just garble the interaction of this secure computation. How do they do that? They publish this sequence of gobble circuits that can talk to each other. A public evaluator, given those sequence of gobble circuits, can emulate the interaction in the way that we have described, which involves in the middle translating the labels using function, reusable functional OT. And from there, they can learn the output publicly. How much time I have left?
You have about 15 minutes, 14 minutes.
Oh, great, perfect. So this basically sketches Mr. NISC overall construction using a very interesting primitive, which is reusable functional OT. So now we need to figure out, okay, can we actually construct the reusable function OT? And we show that we can do that using learning with errors. So recall the task is that P1, P2 have private input, and they want to encode their input in a way that later, by sending a single message, alpha 1, alpha 2, they will be able to reconstruct the choice bit B defined by f of x2, as well as the chosen label where the two labels are defined by g of x1. The overall structure that we're going to use in order to implement those components, there are basically three parts sort of in this construction. The first is that, well, in some sense, I want to be able to, in some way, compute G on the secret input X1 and compute F on the secret X2. So this sort of hints a little bit at homomorphic computation, right, over those encodings. So therefore, these encodings, first of all, X1, we're just gonna be nothing. But X2 is going to be a homomorphic encoding of X2. Here we use specifically a homomorphic commitment, which you can think of as a one-time encryption. So we homomorphically commit to X2 using some randomness R, and it enables a homomorphic evaluation of arbitrary function F, and then we produce another commitment of the output using a related randomness R of F. And here the output is the choice bit. Okay, so basically from the encoding of X2, I can actually homomorphically evaluate and obtain an encoding of the choice bit. Note that because X2 is public, this homomorphic evaluation everybody can do, P2 and P1 both, but only P2 knows how to open this commitment because P2 is the only one who has the randomness. Now, in the computation stage, where we want to sort of enable P2 to give a proof that this commitment indeed opens to the bit B. Why? Because ultimately that the bit B is going to be revealed, that's the output, and P2 must not cheat. So therefore, in some sense, P2's message must be in sort of like a proof that C does open to B. That's Okay, we can do so using a decommitment. But the special part is that I do want to hide P2's private input X2. Therefore, I want this decommitment to be zero knowledge. That it shall reveal the fact that C commits to bit B, but shall not reveal anything beyond the bit B, any other information about X2. So alpha 2 is a zero knowledge decommitment of the commitment C. All right, so the last part is how is P1 going to encode its two choice labels so that we can publicly reconstruct the right label. In order to do this, we sort of want to come up with a special encryption, which we call our witness encryption, for those two labels. And these encryption are special because they are generated. One is generated associated with the commitment to the choice bit and a commitment that this opens to zero. And the other is generated with respect to the commitment and a commitment that, and in some sense, a claim that it commits to one. And in each cases, it encrypts the corresponding label. So what I want now is one correctness, that if I take the right encryption, which has the claim that C commits to bit B, this is alpha 1B, and I have a way to decrypt it using the decommitment that C does open to B to get the right label, because I want to reconstruct the right label. On the other hand, I want a hiding property that the other encryption, which claims that C actually opens to 1 minus B, which is false, shall reveal no information about the corresponding label L1 minus B. Okay, so this is sort of like 3 components in our construction. I want a homomorphic commitment. I want to be able to open this commitment in a zero knowledge way. And I want to design a corresponding witness encryption that will allow me to decrypt when I have a decommitment to the right bit. It turns out that we can do each of the components using LWE. Comes first the homomorphic commitment part. This was already done by prior work by first the JSW homomorphic encryption and then adapted to a homomorphic commitment by JSW15. And roughly, I won't go into the proof of this construction, but just sort of a sketch how these encodings and commitment look like. So there is a public matrix A. It is actually not random. It's going to be pseudo-random and has special structures that I will talk about later. But they're public. And a commitment to a single bit in the input X2 is going to look like A times Ri plus X2 times G, where G is a gadget matrix. By homomorphic evaluation, we can obtain a commitment to the output bit B, and it will look like A times RF plus B times G. Okay, so now we know this commitment can be easily decommitted, right? If I have a commitment to a bit B with this randomness R. Oh, I forgot to mention, it's important that these RIs in the original commitment have random 0-1 entries. And after the homomorphic evaluation, the randomness in the output commitment will have small entries. And the fact that they have small entries is important for many purposes. Now, when we get such a commitment, we know I can decommit to it really easily. I can simply just reveal R. When I reveal R, this will reveal the fact that it commits to bit B. The problem is that this decommitment is not going to be zero knowledge. In fact, R will contain a lot of information about the original X2 that is encoded in the original commitment. So how can I get a zero knowledge decommitment? And here we will start to use ideas from prior work also in JSW, but slightly tweaked. So let's consider this matrix D, which is A concatenated with C minus 1 minus b times g. Essentially, it will look like A concatenated with A times R plus B prime G, where B prime is now a value between -1 and 1. Okay. We know that this matrix, it will look pseudo-random, and we know that it's hard to actually find a short basis for its kernel. In other words, it's hard to find a matrix X where every entries are small and yet D times X equals to 0. Unless I know some trapdoors. Without knowing the trapdoor, it's hard, but if I know the trapdoor, then this can be done efficiently. What are the trapdoors? Either I know the structure of the matrix D, which is I know R, or I know a trapdoor for A. In either of those cases, we have efficient algorithms for generating such a short basis for the kernel of D. And the trapdoor, the short basis sampled using those two algorithms are statistically close. Okay, equipped with this, what we're going to do is we're going to set this decommitment to be this short basis for the matrix D. And the honest party P2 can actually do so because it does know the randomness R. Okay, it cannot reveal R because it will not be zero knowledge. However, if it uses R to sample a short basis, then this short basis will become zero knowledge exactly because the fact that I have a different way of sampling X, which does not reveal any information about R and only need to know essentially what is the original, what is the committed bit B. So the other way of sampling the short basis is the key to giving us zero knowledge property. Now, finally, it comes to witness encryption. We figured that we would like to use this zero knowledge decommitment, which is a short basis for this matrix D, to somehow decrypt some encryption. And here we need to design design the encryption with in mind that I want two properties. When this encryption is claiming the right bit encrypted inside C, then I want decryption to work perfectly to reveal the encrypted label LB. But if this encryption is for a false claimed bit, 1 minus B, then I want this encryption to be hiding, that it should hide the label 1 minus B. And the decryption has to use this short basis, right? This is what we have. And here we leverage ideas from the construction of statistically secure OT from LWE by the work of Braksky and Nikodotli. Sorry for my pronunciation. We're going to use this, again, use some very interesting property of this matrix D. So if I use this matrix D to generate some sort of LWE samples where it has a secret S and perturbed with some small noise E. Given a short basis for D, we can actually uniquely find S. Well, essentially because once I have short basis X, I can annihilate D. So I can get information about E, and from there I can recover S. Well, interesting, right? This sounds like a decryption to me. But I need to see that whether correspondingly will have hiding when the claim is wrong. So the other encryption will happen to be an encoding of S prime with the matrix A concatenated with A times R. So now if I look at this matrix, suppose this A that I said is going to be sampled pseudo-random, but I didn't tell you the structure that it has. Now here is the structure. It's pseudo-random, but it contains many short vectors in its row span. When A has this property, it means that A concatenated with A times R also have many short vectors in its row span. And S prime multiplied with such a matrix plus E is now a lossy encoding of S prime. Great, this seems to suggest there is some hiding. Indeed, from here, we can easily create encryption, which is to extract the randomness using a public seed from S and S prime and use the extracted randomness to hide the label LB. And this will give us the construction of the witness encryption. Okay, so I have described to you the 3 components in the construction. And in conclusion, that we can have Mr. NISC using reusable functional OT. And we think it's a very interesting primitive that we can construct from RWE. And hopefully we can find more application of it, as well as constructed from weaker assumptions like DDH or even CDH, or perhaps generic assumptions. And thank you very much.
All right, thank you, Rachel. That was just really awesome talk, such a cool idea. And with that, we'll conclude this session of the workshop. We just don't have time for questions.
Sorry, I went a little slow, yeah.
That's quite all right. And then we will see all of you in the afternoon.